discussing the events from 318 to 321. There's four presentations I'd like to discuss. First, Davide Scaramuzza from the University of Zurich, autonomous drones. This is a follow-up on Vlad Koltun's presentation, same project, but this time from the lead author, actually, Davide, very interesting, solving perception and planning end-to-end. Event cameras, he introduces event cameras, which we discussed previously, the Omnivision presentation, so the cameras that react on luminance and therefore have much faster reaction times. Second, Sophia Shao from Berkeley, Bears 23. This is a bit of an older presentation, but I had the time to actually go back and listen to it and work a little bit on it. And I think what Sophia's doing is in line with what the computer architecture community is working on, which is how can we design heterogeneous computing system with various accelerators, specialized memory and network equipment to increase throughput and performance of systems. She introduces Gemini, which is an open source design framework that enables flexible design of accelerators. Third, Kate Saenko, again, this is an older presentation, Boston University. She talks about, and there's two papers that she discusses. One is solving the problem of classification in LLMs. So LLMs are fundamentally not structured for classification. They're structured for generation, which is interesting. What does that even mean? Generative video AI is trained to generate, not classify. The difference, generation extrapolates patterns. Classification is based on some sort of nearest neighbor estimation. So these are interesting fundamental concepts that go deep into the latent space and analyze the dynamics of these models. And fourth, Peter Ko, I think that was interesting for various reasons. This is a biostat presentation, and the problem that Peter is trying to solve is find relationships between DNA and the transcriptome. So in other words, how does DNA code transcription factors? The transcription factors are proteins that are coded by DNA and that help code RNA, which then codes for proteins. Remember the fundamental doctrine of biology, DNA, RNA, proteins. So the transcriptome is between the DNA and the RNA, and he's looking for he's looking for deep neural nets, or he's working on deep neural net type solutions for the question, how do we get from DNA to the transcriptome? This is a Not Even Wrong podcast. It's March 25th, 2024. This is Krim Delco. For the day, the fund is up 90 basis points. The market is down 40 basis points. For the year, we are down 16.5%. The market is up 9.5%. We're underperforming by 26%. So discussing the events from 318 to 321, let's talk about Davide Scaramuzza, University of Zurich. So this is a drone project that started a couple of years ago at the University of Zurich. And the problem that they're trying to solve is to create drones that can autonomously fly in a race. So this is a structured environment. Think of it like a race. Maybe it reminds me of ski racing. So you have gates that you have to go through. And what they're trying to do is compete with humans. So this is, in a sense, like the AlphaGo Zero moment for real-world AI, as Vlad Koltun, I think appropriately described it. Davide is not as grandiose. I think he's a little bit more subdued because he's just really describing his project. Very impressive, because what's the problem here, right? The problem here is you have perception and planning in real world AI. These are physical objects flying through physical objects and competing with humans. So in that sense, I think this is new. To my knowledge, this hasn't been done before in any kind of setting with any kind of robot. Maybe there are some competitions in sort of self-driving, but not that I would know of. So what Davide is talking about here is really the problem of perception and planning. And then there's quite a bit of model exploration also, right? What kind of model should we even use? I think they pretty quickly converge to reinforcement learning. That's also, you have AlphaGo Zero that use reinforcement learning with Q learning. So those are still open questions, and I think that's part of the interesting. What I found most interesting about this project is that you have a laboratory experiment in which you can experiment with sensors, with hardware, what kind of inference engine should we even have on those things. You could experiment also on the drone side itself, but that wasn't part of the project. But what you can do most pertinently is you can iterate with the models themselves, and you could again, this wasn't done, you could also iterate on the reward function design. Now what David is doing, he also works with NVIDIA, so surprise surprise, he is doing a lot of sim work. Now the reason they did a lot of sim work is because they literally couldn't destroy many drones. I mean, it's expensive, it takes time, it's dangerous too. So what they did is a model-based, off-policy reinforcement learning algorithm. And you see that source already model-based, so they did create a world model. Now, interestingly, they found out that what the reinforcement learning algorithm converged to was speed and forward perception. I think there was one of the professors at Stanford who asked a really important question, which is fundamentally, the machine is much faster in reactions than human, just physically. I mean, they react in milliseconds. Human takes, I think, 200 milliseconds to make a reaction, but the humans are not that much slower. And the reason is the humans are much better in predicting the next step. So we're pretty good at that. The machines are much faster in reacting. Can we converge? Can we find ways where we can take advantage of the fast reaction time, but add some of the prediction? Another interesting tidbit from the presentation is there was a little bit of an AlphaGo zero moment, because they found out that the reinforcement learning algorithm did actually come up with a new technique, a technique that humans wouldn't do. And the way this worked is the drone would almost do a somersault when turning, and therefore sort of take advantage of physics and geometry and be a little bit faster in taking a turn. Now, that's something that I asked Davide later. It's conceivable that humans could come up with something like that. The problem is, until humans learn how to do this, they would have to destroy many drones. They wouldn't do that. And that's something that the simulator doesn't have, which is it doesn't account for risk. It doesn't take into account the fact that drones can be destroyed, because the simulator doesn't care. You just keep doing until you found a solution, you converge to a solution. So we introduce risk here, risk in the sense that you can destroy the drone, you can also have an accident, things like that. Another interesting thing about the presentation is the strategic interplay, something that's really important with self-driving cars. This drone did not have any strategic interplay with the opponent. It just went faster than the opponent. You could imagine a situation where you have strategic interplay, and where therefore the whole reinforcement learning algorithm turns into a game theory type situation, and therefore a lot more search space on what to converge on. Lastly, I want to mention the event-driven cameras, which is new. That's something that Vlad didn't talk about a few months ago when he gave a presentation at MIT. Now, Davide talks about it. Event-driven cameras are cameras that act on luminance, therefore find out when there's a change in event, and that could also increase the reaction time for the drones dramatically and help in certain applications, particularly with drones that let's say deliver your stuff, DoorDash or Amazon. You could think of, if you have very fast reaction time, you could have a lot more drones in the air, things along those lines. I personally find the technology of event cameras interesting because it's a hardware solution to a problem that potentially could have a combination of hardware solution and software. The next presentation I want to talk about is Sophia Shao, Berkeley Bears 23. This is a computer architecture symposium. She's a professor at Berkeley, and she spoke about a couple of ideas, general ideas, of how to improve computer architecture. Now, the fundamental problem, this reminds me of Mark Horowitz at Stanford and one of the Indian ladies, the professor that the name eludes me now. The fundamental problem in computer architecture is how to have a flexible design to take advantage of heterogeneous compute. What is heterogeneous compute? It includes accelerators into the stack. So an accelerator is not just an accessory to the CPU and is sort of subdued to a computer architecture, an ISA, an instruction set architecture, a microcode that is designed for the CPU or even the GPU. No, we could have a flexible design, a parameterized, flexible, big picture design framework, which is Gemini. That's what Sophia was talking about, where you can fine tune and tweak. So, for example, you could have applications that require several accelerators, almost like a sort of model of experts type solution, where we have an accelerator for detection, an accelerator for planning, an accelerator for this, for that, and then maybe still a GPU to do big, bulky, math, and then maybe we have an accelerator that can take that math and turn it into something more useful. So in that case, we might need some large high bandwidth memory for the GPU, but then we don't need as much memory for the accelerators. Maybe we can fine tune that and use this Gemini platform. So I think Sophia also talks about the scheduler, which is another research area. So she's really introducing several layers of the stack that could be maybe not revolutionized, that's too much of a word, but interesting areas to work on. Let's say that's how I would characterize it. The key problem, according to Sophia, is how to design heterogeneous computing systems with various accelerators, specialized memory and networking equipment to increase throughput and performance of systems. How to make them flexible and adaptive to new model and software architectures. Okay, transformers requires massive memory on chip to execute large dot product multiplications. State-based models like RNN might be less memory constrained, but have more I/O constraints. So those are, like, you can see where this is going, right? What the computer architecture community is trying to do is decrease wall clock time. That goes back to Chris Ray and his presentation in Europe. So we're in that same realm. Onur Mutlu talks about this a lot. We're all in the same boat here. We have a wall clock time situation where we need to reduce that. We have the memory wall. We have power constraints, which are driven by I/O and memory mainly. But on top of that, we have a constraint, which is adaptivity and flexibility, which means that with the proliferation of AI, that is not going to stop anytime soon, we have also the necessity to flexibly adapt our hardware infrastructure to new model architectures. Take multimodal transformers. They will have some sort of, right now where we're living is a transformer type technology with tokenization. So we have a tokenizer that needs to tokenize in probably 3-dimensional space, maybe 4-dimensional space. If we take the RGB and the time, or if we take the Euclidean geometry and time, depending on how you tokenize, and then you have diffusion, which predicts the next sequences. Those are different types of mathematical core functions that need to be executed. And Sophia, in my opinion, really opens up a whole plethora of potential research projects in that field. Third, this is Kate Saenko from Boston University. I picked up her presentation because it has one really interesting point and then one very pertinent point. The interesting one is she talks about the fact that generative models are not very good at classification. To me, that's always very interesting when we have this distinction, because what's on the surface might look at a semantic thing. So classification, generation, so what? Deep down in latent space, it actually has very fundamental reasons why this is that way and this is that way, which teaches you a lot about the actual model architecture and hopefully opens up new doors for solutions to other problems. That's number one. Number two, what she's talking about is also long video prediction, long video analysis, long form video. This is something that Gemini, the Google version that recently came out, also has been able to solve. Now, let's start with the latter. What she's talking about here is context tokens. So the way I understand it is this is a very deep mindish type approach to the solution. So what is video? For now, video analysis, reasoning in video happens in very short clips because we have a relatively short context window, relative to videos. In other words, the context window, which is the amount of tokens that a model can take at one shot when it does inference is fairly limited. For text, it's very large, given what text is requiring to do. But for video and sound, it's not enough. We have a lot more tokens to deal with in video and text. So if we want to have a longer form video analysis or generation, either way, which is similar problem, if you will, then we need better solutions. So what she's doing is she's kind of concatenating shorter forms with context tokens. So what she's doing is she's taking a long form video, cutting it by 10 each, so 10 pieces, and then connecting those 10 pieces and having sort of a self-attention layer of those context tokens so they can refer to each other. And therefore you kind of have like a little bit like a pyramid scheme here, where there's different layers of context that together allow for longer term video analysis. So I thought that was really interesting. On the other problem that she's mentioning, which is the question of classification versus generation, here, fundamentally, why are large language models good at generation? Because their goal is to extrapolate from a sort of self-attention type training set, right? Extrapolation means find relationships between the prompts and a potential future trajectory, some sort of variational inference. Versus if we look at classification, that's more of a nearest neighbor type problem. Now, of course, eventually it converges to a similar type of problem, which is, okay, how is this similar to that? And whether I'm asking about positioning or relevance or just pattern or extrapolation, it's kind of, in a sense, the same thing. You're asking for similarities, for patterns, but fundamentally, mathematically, or in a vector sort of world, it looks very different. The generative video versus classification. So that's what Kate is pointing out in her paper. I didn't go deeper here, but I just thought it's worth mentioning that there is actually a difference between classification and generation, and that LLMs can be also trained in particular for classification, whether it can be done in context or whether we actually have to change the parameter space. That remains to be seen. This is a further research that Kate and her group are doing. Lastly, I want to talk about Peter Koh. Now, Peter Koh's presentation, he's at Cold Spring Harbor Lab. He's a biostatistician. And the problem that he's trying to solve is he's looking, what's the relationship between DNA and transcriptome? The transcriptome are transcription factors that capture the sort of the code that is needed to encode RNA. So we go from DNA to transcription factors. The definition of transcription factors is just they play a crucial role in controlling gene expression by binding to specific DNA sequences in the regulatory gene sequence of genes, and then they define mRNA, which is the part of the sort of gene expression pipeline that goes then creates RNA and then protein. So think of it like if we have DNA, RNA, protein, it's between the DNA and the RNA. So what happens there is DNA creates a certain, is a code that then creates a transcription factor, which creates mRNA, which creates RNA, which creates protein. So in the end, what the transcriptome does, it gives you a sense for how DNA codes for a subdivision of the end product, which is the protein, which is the workhorse of biology. So what Peter is talking about here, I thought it was really interesting the way he presented this, because here's a couple of things that I paid attention to. Number one, he did a little bit of model exploration. So he started with the idea we use deep neural nets and found out that actually very simple, almost one-layer nets, I think he even said that, you don't need deep neural nets to capture most of the information. Now, that doesn't mean there is not enough information. I think what it just means is that deep neural nets, the architecture that he used wasn't really very good in capturing the complex information available. So there is more model exploration to be done. And this reminds me fundamentally of the problem, let's say, in finance is like that, right? If you take time as a concept in finance now, and you tell yourself, okay, what is the time frame that I'm looking at? Most predictive functions in finance are a function of time. In other words, I can tell you in the long run what factors predict wealth creation. And one of the major ones are interest rates. That's in the long run one of the most important factors in returns on, let's say, in the equity market. So if you can predict, and I don't know what the exact, I think maybe if you can predict 6 months ahead what the 10-year yield will be, you have a very good chance to have outsized returns in the stock market measured on a yearly basis. So it's about interest rates, but this is on the long run. You can also do pretty well on the short run, which is what most of the flash trader, algo traders are doing. So in the millisecond space, you're also pretty good, because in the millisecond space, what you're exploiting is usually liquidity risk, mean reversion, things like that. But where there is a problem, if the time scale is 9 to 12 months, all of a sudden you're looking at, because even there interest rates are maybe not as crucial, to see whether Microsoft or Uber or Tesla will do well in the next 9 months. The 10-year is not going to give you a lot of information. So here you have a little bit more complex relationships that are relatively hard to find. I think the statistical and computational finance community is still working on these solutions. So this reminds me a little bit like the same with this transcriptome project here by Peter Koh, which is like you do have certain information that can be captured with very simple models, but you also have a lot more complex relationships that so far have not been captured. Now, this is my feeling here, this is my gut feeling, that actually this whole DNA, transcriptome, RNA type space can be captured much better with self-attention type transformer technology, because it really is about positioning, it's about relative positioning, it's about what influences what. So in that sense, it has similarities to text. A word does depend on where it stands, and it does depend on what's previously, what comes after. I love you, the word love really matters, and the word I matters for the word love. I hate you, that the word I has a very different meaning than in the love, and the word you has a very different meaning semantically. So positioning and relevance, the word I hate you a bit has different meaning than I don't mind a bit, or like these things all matter. And I think in that sense, LLMs, where they are today, can actually help quite a bit in this particular problem, in general in biostatistics. So this is something Jensen was talking about at JP Morgan 24. This is something he's talking about a lot in almost every presentation. Now, healthcare is a frontier that can be tackled with large language models, and in particular also with in silico design. As a summary, the 4 events, number 1, Davide Scaramuzza, autonomous drones, the problem of perception and planning, event cameras, how to incorporate them into a better solution for fast, accurate planning, model-free or model-based RL type-driven robots. So this is really an interesting project that I think warrants more research and is really interesting from that perspective. Sophia Shao, she is at Berkeley Electrical Engineering, talking about computer architecture and the need for flexibility given the heterogeneous compute platforms that are going to be more important. And she introduces Gemini, a flexible framework that allows for fine-tuning of computer architecture design. Kate Saenko, she's talking about 2 types of problems in LLMs. One is the classification versus generation, and the other is long-form video reasoning. And lastly, Peter Koh, who mentions, he's a biostatistician talking about the relationship in DNA and transcriptome, and also about model exploration in that space. Thank you.